All right, so welcome back. We are going to continue talking about um, uh, reactions of how we can make alcohols. One of the things to keep in mind is that uh, as you start trying to make more complex molecules, one of the things that comes up is that you have to really think about the reactivity of other parts of the molecule when you're trying to use it. So what I mean, for example, what I mean by that is, for example, let's say you take this alkyl halide here, which is so I can go. Let me go to full screen. Let's say you take this alkyl halide here and you react it with magnesium to make the Grignard reagent. Not, you might be like, that seems reasonable. So if I make the Grignard reagent here, what that's going to look like is it's going to look like this. 1, 2, 3, 4. And then you might think, okay, I've made this Grignard reagent, and then that Grignard reagent, so I'm going to redraw this as the R minus. That's equivalent to this. 1, 2, 3, 4. So you make the anion here, and you might think, oh, well, then this anion is going to attack my carbonyl carbon, kick up, protonate to make the alcohol. But there's a significant problem with trying to make this Grignard reagent. Keep in mind that when you make the Grignard reagent will react immediately with any acidic proton. And the proton on this alcohol is acidic. So that brings up a really important thing to keep in mind when you're making Grignard reagents. You can't make Grignard reagents of molecules that have acidic protons on them already, right? Like, I can't make the Grignard reagent here. Also, I can't react the Grignard reagent with an aldehyde or a ketone. So let's say, for example, I wanted to react a Grignard reagent with this aldehyde. I would need at least two equivalents of the Grignard reagent, one to deprotonate the oxygen here, and then one to react, okay? So you have to keep in mind the different parts of the molecules. You have to keep in mind like all of the molecule when you're reacting, okay? So when you use a Grignard reagent, two things. One, when you make a Grignard reagent, the Grignard reagent can't have any acidic protons. Also, if you try to react a Grignard reagent with an aldehyde or a ketone or an ester, and it has an acidic proton, and that aldehyde, ketone, or ester has an acidic proton, you need as many equivalents as acidic protons, plus one more or two more, depending if you're using the ester, for the aldehyde or ketone. Now, that doesn't mean that we can't make the Grignard reagent of a molecule. That doesn't mean we can't make a molecule like this. All that means is that we have to figure out a way to basically mask the alcohol, to protect the alcohol. So what we want to do is we want to take this molecule, we want to do something to protect the alcohol, to mask it. We want to perform the Grignard, we want to make the Grignard reagent, do the Grignard reaction, and then deprotect, all right? There are and so these are called protecting groups, and there are numerous protecting groups out there. There's actually like really, really thick books of protecting groups. When you do complex molecule synthesis, a lot of the time that you spend in doing complex molecule synthesis is changing protecting groups. And it turns out that there are protecting groups that will fall off in the presence of acid, base, neutral conditions, light. There's a whole myriad of ways to protect things and deprotect things. What we're going to go over is the use of something called trimethylsilyl, the trimethylsilyl protecting group, or TMS. So if I take this molecule, I can put on what we call the trimethylsilyl ether. The reason it's called trimethylsilyl, so there's three methyl groups, trimethyl, silyl for silicon, and then it's an ether. It's kind of like an ether where this oxygen is bound to a carbon, but instead of this oxygen being bound to another, it's a silicon, so it's a trimethylsilyl ether. So this is usually abbreviated OTMS. And the way you put the TMS group on is you take an alcohol, you take TMS chloride. So notice that this silicon is bound to a chlorine in the presence of a base. And then it's basically an SN2 reaction between the oxygen and the silicon to put the TMS group on. Now you might be wondering, you might look at the silicon and be like, Raja, that silicon, it's tertiary. There are three alkyl groups. It's kind of like a tertiary carbon. How are we doing an SN2 reaction on that tertiary center? That's a really good question, student. And the reason you can do this reaction is because the size of silicon, right? This is also one of the reasons why we're carbon based and not silicon based. Like silicon can make 4 bonds, but the size of silicon is such that those 4 bonds it makes, it likes to make bonds to oxygen, whereas carbon can make like stable bonds to itself and hydrogen and oxygen and nitrogen and phosphorus, all kinds of different things. But when you look at because silicon is bigger here, right, what we find is that even though there are 3 alkyl groups here, that the backside, the antibonding orbital of the silicon makes the backside, or the antibonding orbital of this silicon halogen bond is more available for attack, right? So this is where I'm just trying to bring in some more of that molecular orbital theory. So the backside attack can actually happen more because the silicon atom is a lot bigger. Now, once you put the TMS group on, we can take the TMS group off either in the presence of acid or F-. So it's the reverse of, so taking it off mechanistically is the reverse of putting it on. Usually you try to avoid fluorine. You can use, but if you do use fluorine, the most common form of fluorine that's used to remove the silyl group is TBAF, tetrabutyl ammonium fluoride. The reason why this works is because the fluorine-silicon bond is really strong. So fluorine likes silicon a lot. So if you add F-, it's going to attack that silicon right away and kick out the oxygen. Now, there are a number of different silyl protecting groups that differ in their size, and that the size basically affects how stable that protecting group is. But we're just going to really deal with the TMS protecting group. So if you want to think about how to use this as a Grignard reagent, so if we go back and revisit the process we were going over, you take your bromo alcohol, you react it with TMS chloride in the presence of triethylamine, a base. That puts the TMS group on. I can now make the Grignard reagent that's going to insert in here to make the carbanion here. This carbon will then attack that carbon, kick up, protonate to make the alcohol. So I notice I've elongated my molecule by 1 carbon. 1, 2, 3, 1, 2, 3, 4, right? That fourth carbon is here. So I'll just go ahead and write this out. So the magnesium is going to insert, right? So I make my Grignard reagent now. I want to think of that Grignard reagent really as the carbanion, right? So I'm going to think of this as the carbanion. The carbanion is going to attack my carbonyl. So that's going to have extended my molecule by 1 carbon here. Whatever the R groups are, it doesn't matter. And then I'm going to protonate with water. I'm going to protonate the O- with water to give me my alcohol, okay? And then I can deprotect with TBAF to give me my diol. So this is another way to make diols, right? By using these protected bromo or chloroalcohols. All right, so let me know if you have any questions. I hope that all made sense. Look at some problems in your book, and then let me know if you have any questions. Thanks, and have a great day.